Now let us discuss about the very important point in the surface integration. Let us discuss about how to write the ds. In line integration, we have integrated with respect to dl. The differential element there was the infinitesimal length, very small length. We call it as a dl. Similarly, here in surface integration, our differential element will be a very small surface, infinitesimal surface, and we will call it as ds or sometimes dA. So let us discuss about it, how to write it and how it is found out. My dear, in previous lectures we have seen about the representation of lines and planes and surfaces. Can you recall it? We have seen about the lines that for any line we have two coordinates constant. Only one is variable for that line. This is how the equation of line looks like. For the surface, we have seen that for any surface we have only one coordinate constant, while rest two are variables. So this is how the equation of surface. One coordinate equal to constant. My dear, I have warned you there also, and once again I am warning you. This is not the universal way to talk about the lines and planes. The lines and planes can be more complex also. But this complex portion, we will deal with it in the later part of our syllabus. But as if now, it is completely okay to remember like this. My dear, this part I have discussed in very much detail in the lecture of coordinate systems. You can easily go through it. But once again, let me reiterate some of the portion of it. Consider x equal to 4 plane, as you can see from the diagram. As I just said, any surface or plane is represented with the equation one coordinate equal to constant. Only one coordinate equal to constant. So in our given surface is x equal to 4. X equal to constant. As you can see from the diagram, the x equal to 4 surface is parallel to yz plane. And if we consider any point on this surface, any point, you can easily notice that each and every point is at a distance of 4 from the yz plane. Actually, what is the x coordinate? Can you recall the definitions of coordinates that we have seen in the previous lectures? X coordinate is the perpendicular distance from the yz plane. So in our diagram, each and every point on the given plane is at a distance of 4 from the yz plane. So each and every point will have x coordinate equal to 4. So you know, for any surface, the surface is parallel to yz plane. So for this surface, x coordinate is equal to 4. X coordinate equal to constant. But for different points on this plane, let us say point x and y, you can easily observe that for different points of this surface, we will have different y and z coordinates. So what I am trying to tell you, for any surface or plane or area, we have one coordinate constant. Rest two, they can be variables. Actually, what is the area? Area is normally length into breadth. We can get the surface or area only when two coordinates, two lengths are changing simultaneously, while other one must be the constant. So for any surface or for any area, out of three coordinates, we must have one coordinate constant, rest two must be the variables. As we have defined the differential length in line integration, here in surface integration, we will need the differential surface, ds, the infinitesimal surface. So consider once again x equal to 4 plane or x equal to 4 surface. Let us assume that we are integrating over this surface x equal to 4. Now my dear, we want a very small area infinitesimal area, infinitesimal surface from this given surface, and that will be our ds or dA. Now you also know that for any surface or for any plane, we have one coordinate always constant, rest two are variables. For example, given surface is x equal to 4 surface. So for this surface, x coordinate is going to be constant. Every point on this surface will have x coordinate constant. Only y and z coordinates can be changing. So my dear, how can we get a small area on this surface? Recall that normally area is length into breadth. So we will at least need two lengths to get the area. So my dear, as you can see from the figure, to get the very small area from this surface, we have to take a very small length, differential length along y, let us say dy, and we have to take a very small length along dz, differential length, that is dz. So our required small area on this surface will be dy into dz. So my dear, for this given surface x equal to 4, our differential surface, our differential area ds will be dy into dz. Now my dear, you also know that area of the surface in electromagnetics is not a scalar quantity. It is a vector quantity whose direction is perpendicular to own surface. So here we have to put one unit vector. Now the given surface is x equal to 4 surface. You know, x equal to constant surface is parallel to yz plane. So perpendicular to this plane will be, obviously, as you can see from the diagram, will be in the direction of x, maybe positive x or maybe negative x. But perpendicular to this surface will be in the direction of x. So our unit vector can be plus ax or minus ax. So my dear, the differential surface for this given surface x equal to 4 or x equal to constant will be ds equal to dy dz plus minus ax. Similarly, had I considered y equal to constant plane for my discussion, we would have got ds equal to dx dz plus minus ay. Similarly, ds for the z equal to constant plane will be dx dy plus minus az. So you know my dear, this is very simple pattern to remember. You can easily remember it. For which surface you are integrating? X equal to constant, then ds will be like this. For y equal to constant, for z equal to constant, it is the simple pattern. But my dear, we will write the expression of ds from the expression of dl. We have seen the expression of dl, differential length, in the lecture of line integration. The dl in the Cartesian coordinate system is given as this: dx ax plus dy ay plus dz az. So you know, we will write the ds, differential surface, using this expression. This is kind of shortcut technique. For example, let us say I want to write the ds for x equal to constant plane. You know that for x equal to constant plane, ds is going to be dy dz plus minus ax. Am I right? So let us see how we write ds from this expression. X equal to constant. That means you cannot integrate with respect to x. It is going to be constant. So from the expression of dl, drop the term dx, take the unit vector of that, add plus minus sign, multiply the other two differential lengths. My dear, you can easily see from your screen, you will get ds equal to dy dz plus minus ax. Isn't this interesting? Let us take one more. Let us say you are writing ds for y equal to constant plane. So once again look, drop the dy, y cannot change, y equal to constant plane. Take its unit vector, add plus minus sign, multiply other two differential lengths. So ds will be dx dz plus minus ay. Similarly, you can easily try for z equal to constant plane, dx dy plus minus az. You know, my dear, this method we should apply for each and every coordinate system. We have cylindrical coordinate system, spherical coordinate system. You already know, in cylindrical coordinate system, the dl is given as you can see from the screen, d rho a rho plus rho d phi a phi plus dz az. So let us say we want to write the ds, differential surface, for rho equal to constant plane. Look carefully the expression for dl. We want ds for rho equal to constant plane. So drop the d rho, take its unit vector, add plus minus sign, multiply the other two differential lengths. You will get your ds. So the ds for rho equal to constant plane will be rho d phi dz plus minus a rho. Similarly, let us take one more. Let us say we are writing ds for phi equal to constant plane. Phi equal to constant. So drop the differential length for phi. The differential length for phi is rho d phi. Drop it, take its unit vector, add plus minus sign, multiply other two differential lengths. So the ds for phi equal to constant plane will be d rho dz plus minus a phi. Similarly, you can easily try for z equal to constant plane. It would be rho d phi plus minus az. And on the same way, you can easily write all the differentials for r equal to constant, theta equal to constant, and phi equal to constant of the spherical coordinate systems, as you can see on the screen. Now let me recap all the things that we have seen in surface integration. My dear, we require a surface integration when we need a flux of the field that is passing through the given surface. And by the way, what is the flux? It is the normal component, the perpendicular component of the field that is passing through the surface. So in such case, we require the surface integration. It gives us the flux. Always remember, the area of the surface in electromagnetics is a vector quantity. Magnitude, as you already know in our mathematics formula, if it is circle, pi r square, if it is rectangle, length into breadth. Magnitude will be same as we know, but its direction will be perpendicular to its own surface. There can be two directions, this way, that way. Which way we should take? That will be clear in later part. But as if now, surface or area is a vector quantity whose direction is perpendicular to the given surface. And very important, the surface on which we are integrating, for that surface we have one coordinate constant and rest two are variables. The coordinate which is constant, drop that differential length and take the multiplication of other two differential lengths. That is how we write the differential surface ds for any surface in the surface integration.